Hello everyone, my name is Ida Ayu. I'm a graduate student at Sungkyunkwan University and Professor Jee-Hyong is my supervisor. On this occasion, I will present my paper that has been accepted as regular paper at the 2020 Research in Adaptive and Convergent Systems (ARACS). The title of this paper is Sequence-to-Sequence CycleGAN for Non-Parallel Sentiment Transfer with Identity Loss Pretraining. In this paper, I tried to perform a natural language processing task called sentiment transfer, which includes text generation based on target sentiment. Most text generation tasks in natural language processing are done using sequence-to-sequence models trained on a parallel dataset. However, many text-style transfer tasks, such as sentiment transfer, doesn't have such data available, and building a parallel corpus for training specific tasks is labor-intensive. Therefore, unsupervised text generation methods that require only non-parallel data are appealing and gaining attention to address this problem. Sentiment transfer is one of text-style transfer tasks which aims to change the underlying sentiment of the source text while preserving the non-sentiment content. A sentiment transfer model receives an input sentence with positive or negative sentiment and produce output sentence with the opposite sentiment. For example, a positive sentence, "The room is clean and neat," is transferred into negative sentence, "The room is dirty and messy." The goal is that the output sentence reflects the target sentiment, which is negative, and at the same time, it also needs to keep some amount of source content or context, where in the example, it should keep the room as its context. The amount of source content preservation can be reflected by the Putu score between original and the transferred sentence. The common approach used to perform these tasks is by building an autoencoder model which learns disentangled Latent representations and then use controllable style attributes to transfer the target style information. The sentiment transfer model is trained in unsupervised manner using non-parallel dataset. Xian et al. Addressed this under-constraint problem using cross-aligned autoencoder. The encoder E tried to separate the content of the source sentence from its sentiment style, denoted by Y, and produce a disentangled latent representation Z. This approach assumes that the two sentence population, positive and negative, have the same distribution of content set when their sentiment style information is eliminated. The disentangled latent representations of source sentences produced by the encoder is then fed to the decoder G along with the target style variable. Xian used an RNN-based decoder with a fixed length vector representing the target style as initial hidden state of the RNN. The sentence produced by the decoder is fed to a real-fake classifier which corresponds to its target sentiment. They have one real-fake classifier for each sentiment that act as discriminators to perform an adversarial training. Instead of training a binary classifier to align the source and the target sentence distributions, Yang et al. Used language models as discriminators. So they fed the softmax probability distribution of the transferred sentence to the corresponding language model. The loss of the discriminator is computed as cross entropies between the softmax probability distributions of transferred sentence and the discriminator outputs distribution. Following the previous methods, Fu et al. Also work with single encoder model. They then use multi-decoder to control the sentiment style of the generated sentences. By building a style-specific decoder for each sentiment style, they reduce the need to learn a style attribute representations like style embedding method, which is also evaluated in their experiments. Despite the success of previous works in producing transferred sentence with the target sentiment, These models tend to suffer in preserving the non-sentiment content. For example, a sentiment transfer from negative to positive sentence performed by Xian et al. It transformed the source sentence, I hate mayonnaise, into I love a vegan Jones, I love their wife, a Anand. This sentence has the correct sentiment, but does not preserve the original content. Most of the transferred positive sentences contain the word love or thanks, which boosts the sentiment accuracy. To manage this content preservation while performing sentiment transfer, we propose a sequence-to-sequence CycleGAN model and pretrain the text generator with identity loss pretraining. CycleGAN has shown promising performance in image domain to perform style transfer with non-parallel dataset. CycleGAN for non-parallel style transfer is built using two different generators and discriminators. The original CycleGAN generator and discriminator were implemented using several convolutional layers for image style transfers. To adapt with the sequential characteristic of a natural language, we implemented the CycleGAN generator as a sequence-to-sequence model using LSTM networks. The styles in sentiment transfer are defined as positive and negative style. In the following figure, the negative to positive generator T and P transforms real negative sentence N into generated or fake positive sentence P apostrophe, while the positive to negative generator TPN does the opposite transfer direction. TP and the N are real fake classifiers of positive and negative sentence respectively. For the generator TNP and discriminator DP, the generator aims to maximize the adversarial loss as in the common GAN model, while the discriminator is trained to maximize the loss. The similar adversarial loss is applied to the generator TPN and discriminator DN. A well-transferred sentence should be able to recover to its original sentiment style. To ensure this property, the text generator is trained in a cyclic manner as shown in the following figure. In the cycle training using real negative sentence N, this N is transformed into fake positive sentence P apostrophe using generator T and P. This P apostrophe is then fed to the generator TPN, producing a transfer sentence N apostrophe, which is a fake negative sentence. The resulting N apostrophe is compared with the original sentence N to measure the recoverability. A single cycle training is not sufficient and not stable for this under-constraint problem. Therefore, the same cycle method is applied for real positive sentence P. Instead of using L1 norm as in the image style transfer, the loss of the cycle training is computed as cross entropy between vector representation of the real source sentences and the probability distributions of recovered sentences. The full training objective is the combination of adversarial loss and cycle consistency loss with a constant lambda applied to the cycle consistency loss to control the importance of cycle consistency in the training objective. The goal of sentiment transfer is to change the sentiment information of the source sentence while preserving the non-sentiment information. To avoid the model from merely transforms most of words in source sentences into sentiment words, we pre-train the text generators with identity loss pre-training. The text generators are treated as autoencoders. We then compute the identity loss as cross entropy between input vector representations and the probability distributions of the output sentences. We compare our CycleGAN model in two different settings, with and without the identity loss pretraining. Following Xian et al. And Su et al., our experiments were conducted using the Yelp review dataset, which consists of unaligned positive and negative sentences. We then perform automatic evaluation on the resulting model to measure the transfer performance objectively. Sentences generated by our model were evaluated on the accuracy to measure the effectiveness of sentiment transfer. The accuracy was calculated using pre-trained sentiment classifier as in Xian et al. Experiment called TAG-CNN. Although the tag is called sentiment transfer, a very high sentiment accuracy cannot ensure the model to produce a desirable transferred sentence. Therefore, a blue score is measured to evaluate the content preservation. We compute the blue score between the transfer sentence and the original sentences. As the model tries to improve the blue score, the sentiment accuracy may drop in a certain amount. And it is hard to compare the model's performance since some models have higher blue score but lower accuracy than others. T-score or geometric mean provides a comparable overall performance metric for this trade-off, which also used in the previous work. Therefore, the overall performance of sentiment transfer model is measured as geometric mean between the model accuracy and blue score. Models with higher T-score are considered to produce a better transferred sentence. As shown in the following table, the CycleGAN model produced a high sentiment accuracy without the identity loss pretraining. However, it has a low average blue score compared to others. The model with low blue score produced transfer sentences which mostly repeat sentiment words in the target style and do not preserve the original context well. For example, a source positive sentence, good food, good service, and good prices, is transformed into negative sentence, terrible, terrible, terrible. Performing generator pre-training using the identity loss improves the model's blue score, which indicates the transferred sentence preserves more content from the source sentence. The overall transfer performance, or T-score, is also improved from 13.15 to 50.69. This result shows that the identity loss pre-training together with the CycleGAN training objective play a critical role in achieving better transfer performance. The model results in a better transferred sentence as in the following table. The average blue score obtained by our best sentiment transfer model is 32.02. The transferred sentence with blue score around the average blue score effectively transfer the target sentiment attributes while preserving the non-sentiment content. When the blue score is relatively low, the transfer sentences sometimes change the non-sentiment word, causing a context change. For example, a source positive sentence, best potato cheese soup ever, is transformed into worst curry chicken ever, with blue score of 19.48. Although the sentiment of the sentence is successfully changed, the object potato cheese soup is also transformed into curry chicken, which changed the original context. Improper transferred sentences also obtained when the blue score is relatively high. Transferred sentences with blue score above 90 almost did not change any source words, causing poor sentiment transfer and reduced the model accuracy. From a series of experiments we have been conducted, it shows that the proposed sequence-to-sequence CycleGAN, together with the identity loss pre-training, play a critical role in achieving better transfer performance. It improves the model's blue score and obtains the highest overall transfer performance. The sequence-to-sequence CycleGAN model can be later improved using more sophisticated methods, such as an attention mechanism, to better recognize the sentiment and non-sentiment words. It may also help the text generator to transform and to preserve correct information. That is all for my presentation about the paper. Thank you for your attention.